Hello there. Welcome to an interesting problem, the problem of Foucault pendulum. So let's understand what Foucault pendulum is, and then we'll get into more mathematical description of Foucault pendulum. So Foucault pendulum is a regular pendulum. You just hang in. You hang in so that the pivot or the place you hang in, it can actually rotate as the plane of the pendulum is rotating with time. Okay, so if you might have seen this in some museums, very tall. This effect is more pronounced when you have a very long pendulum, and sometimes in a rotunda of a building, people just hang one, and the pendulum will just swing back and forth, but it doesn't go through the center. It seems to, when you come back a little bit later, it's going to go in a different plane than it was going earlier. So what is the relation of that? That happens because the Earth is actually rotating. You can prove it mathematically using Newton's laws. That is because of the rotation of the Earth. That's one of the ways. Actually, if you were in a frame which is rotating, one way to tell it is just build a Foucault pendulum, and then you'll be able to tell that you're actually on a rotating frame. Okay, so if angular frequency, which is angular frequency any omega, is 2 pi over time period. So of Earth is, say, this is the angular frequency which is Earth is rotating about fixed axis through the center of the Earth, So we're just gonna take it like this, and if it's rotating, then you'll see that the pendulums, the Foucault pendulum, the plane of the Foucault pendulum is rotating. Plane of the pendulum is rotating with time, and in the northern hemisphere, it's going to go clockwise. In northern hemisphere, and counterclockwise in southern hemisphere. It's like if you're doing the experiment in say northern, maybe in Europe or even India or China, you will see clockwise. If you're doing the experiment in Australia or New Zealand, you're going to see it do counterclockwise. Okay, and that because it has to do with the main effect is Coriolis force. We will see. Okay. And precession, this rotation is called precession, and precession frequency is related with the angular frequency of Earth in this way, and you can convert that into time by 2 pi over the same formula for this precession frequency, and you can so like this will be time, Earth will be omega Earth. 2 pi over omega Earth. So you see the precession frequency is inverse of sine lambda. Lambda is latitude of the place you're doing the experiment. Of course, lambda shouldn't be 0, otherwise this thing is undefined. So if you get closer to the equator, you get the longer you have to wait to see any change. More to the, if you go to the North Pole, it will, so lambda equals 90 degrees, and precession, so this will go around full circle in 24 hours. If you're at 30 degrees latitude, it's going to go around 48 hours. Take 48 hours to go around. Okay, so how do we understand this? So that's what we want to do in the rest of the video. So to understand that, we'll look at the problem in a more detailed way. So here is a situation. You have this like I'm going to take Earth as a sphere, although it's not a real space. Like it's forward a little bit flat at the two north and south, but we're just going to take it as a sphere for simplicity, and we are going to have actually inertial frame. You can do inertial frame like this, like I've drawn here, but I'm going to actually do this over here. So this will be the frame, and yi. So I will write the bottom has to do with inertial coordinates. Okay, and I'm going to use non-subscript I for rotating the frame that we're going to use on our lab, which is this frame shown in blue. So what is that frame? That frame is a local frame. So if I'm at that, let's say O, that's we're going to do the experiment, then tangent to that plane, that's the flat Earth I'm going to see. So that's going to be tangent to Earth. So this is a flat tangent plane. This is a flat. And over there, I'm going to draw tangent to this this circle, which cuts at lambda, that latitude. So it's a cross section of the Earth, and it's tangent to that is going to be my east. So this is east-west line, and if I do a great circle this way, tangent to that will be the north-south line. So this is going to be my north, and this is my south. Of course, south is here, but that's in the tangent plane. It's a plane. Imagine having a flat surface just touching the Earth on that point. And so we're going to define the axis that way. You don't have a, Cartesian axes are not curved, so you're going to have to define like a straight line axis, and up will be just straight up, and this will actually go right through the center of the Earth. Okay, so this would be my X, Y, Z, and you can see this frame is actually going around the Earth. In 24 hours it comes back to this original orientation. So it's actually rotating and translating. So it has two things we have to take into account. So if I look at a particle, some particle P of mass m, its equation of motion with respect to the inertial frame will be just this. So in the inertial frame, and we'll show, actually we have shown some of this before, that this, if I were to write instead of xi, yi, and zi, if we want to, this point P, its coordinate will be xi, yi, zi in inertial frame, and it's going to be x, y, z in a non-inertial frame. The relation between them, you can see over here the vectors are, this is the relationship, vector relationship is written down. This relationship, I can actually do the derivatives and all kinds of stuff is shown in another video. So it will be, this can be shown to be the acceleration for this coordinates plus this effect due to rotation. This is due to rotation of frame. And then if it's translating, the frame is translating, and it's also accelerating in translate way. So you can think of this, what's the acceleration here is going in a circle. So there is a centripetal acceleration. So this acceleration of the frame, this is a frame, is centripetal acceleration of point O, or the origin of the frame. So frame is rotating. You say, frame, how do you know this frame is rotating? Well, because the Earth is rotating, you can actually show that if I were to just bring this axis over here, and then if I go a little bit further over there, these guys, the frame itself has tilted a little bit with respect to the same line. So it's at different points, the frame is actually pointed in different directions. And you can show that the rate at which this is going is the same as if you were to put this guy right over here and just monitor with time. All right? Okay, so with that, we would want to set up what we're gonna see for a pendulum. All right? Okay, so now I've drawn some axes to help us with the calculation. So that's the original setup, and now I've become more concrete. There's the pendulum, and where's the bob here? I have point P, and I put axis at the hanging point, and I drawn XY in two different places just so that I can kind of show you the angle that will be following for the precession. Okay, so you can now implement these equations. So we need to look at the forces. There are two forces, and this Fg with the capital G, because it's actually Fg is G Newton mass of Earth over radius of Earth, almost, right? Because this pendulum is very close to the Earth, and the difference between radius of the Earth and a little bit above Earth is not very much. So we just magnitude like that, and if you let's write this down. So we have a Fg. These are real forces. So this is not mg. Okay, this is real force. This is kind of effective things that we see. All right. So we'll come to that. What's the relationship between this and mg? Where the mg comes in. Okay. So Fg plus the tension should equal to all of this right side. So this equals to this acceleration in the XYZ coordinate, not the inertial coordinates, right? This is equal to let's divide by mass. So don't have to mass in everything. Divide by mass. Then I will have a acceleration. So this acceleration will be x double dot I hat plus y double dot j hat plus z double dot k hat, and k hat will be that way, I hat will be that way, j hat will be that way for us. And then we'll have 2 times this is a Coriolis force. So V will be x dot I hat plus y dot j hat z dot k hat, and then you'll have a omega cross r. So what is r vector? R is x I hat plus y j hat plus z k hat. Plus we have a omega cross omega cross r. So this for the translational motion of the frame around in this circle. Okay. First note is that these two are, this r is this distance, and so r is radius of Earth, and this is lambda, so cosine lambda. So unless I'm right on the North Pole, this is much bigger than this distance from here to here is that's the r, which is the length of the pendulum. This is the length of the pendulum. So magnitude of this guy is like omega square L, and this is like a omega square radius of the Earth, as long as the lambda is not very close to 90 degrees. If lambda is not 90 degrees, so maybe lambda 60 degrees, say. So that's going to be half the radius of the Earth, and your pendulum is not going to be that big. So between these two, when you add them up, this can be omega cross radius of Earth cosine lambda, so something like that. So you can see that this is kind of like a constant thing, and we can try to see if there is a way to look at it so that we can connect with the mg. So this stuff will be defined as a g vector. It will be effective g vector. So we'll get a effective g vector plus t over m, the acceleration of the particle, plus 2 times omega cross v. And the g will be simply whatever the Newton's law tells me, divided by mass of the particle minus omega cross radius of the Earth, approximately radius of Earth from and cosine lambda. So this would be, say, if I had this direction in this, let's call it rho hat. So this whole thing will be approximately is going to be omega square radius Earth cosine lambda rho hat, and this will be along the center. So this will along the center of the Earth. So this will be g Newton mass of the Earth plus radius Earth is square k hat. So minus this, and this becomes a plus. So you can see the g is not along, this new mg that we use is not along really this direction or this direction we write normally. It's a little bit different. So you can say, oh, how much different? Let's look at some magnitude, some numerical value. So numerically speaking, for this, let's say lambda is, because we need to cosine lambda, let's call it 60 degrees for easy calculation. And you plug those numbers in. So this is the omega of the earth square. So omega of the earth, when you look at this, omega is omega of the earth. So omega of the earth will be 2 pi of the time period of the earth. So plug in there, you find that this is, close to 10 with a minus, that's minus 10 meter per second square. And this stuff is plus 0.02 meter per second square. So very different. It's very small effect. So we can just kind of ignore it. We can say G is minus G k hat. K hat is up, the G will be down. So we're going to just say G is that for us when we do the calculation. Okay. So with that, let's see what this equation looks like when we set it up completely. Okay. I forgot to tell that this kind of derivative relationship between rotating frame and inertial frame is what was used to actually get this rotation formula. You should look into a previous video I did for physics in the rotating frame. Okay. Okay. So I've got some geometry here I had to draw to show which way the vectors are. So the omega e vector, if it's rotated this way, then we define an angular velocity vector pointed in that axis, along the axis of rotation, right? You probably know that from before. So you can kind of resolve this on the k hat direction and along x and y direction. And this will be, it's a this will depend on, I hat and j hat directions actually are in the space they're changing, right? So but their sum should be, the whole thing you can write down omega horizontal. So this is the omega vertical, and you can write down this thing as a vector, this whole thing. So if you this is the equation of motion, let's resolve into x, y, and z components. Just maybe you can do it blindly, but maybe some simplification will help. Prior simplification, one can say, is that in a pendulum, this motion in the horizontal distance is way greater than the vertical distances for the same amount of time. So z double dot, ignore them, compared to x dot, x double dot, y dot, y dot. So these are the only things you keep in time derivative. So if you look at over here, this is the only one that I need to work with. This is along this we already have minus g k hat. So this minus and minus will become a plus, and this t will be tx I hat plus ty j hat plus tz k hat. And tx, you can look at here, is pointing in the negative direction. So if you project, the t is pointed in that direction. So this will be minus x over L times t I hat, and this will be minus y over L t j hat, and this will become this distance L minus z. L minus z over L times T k hat. So this very easily resolved. This is, I've already written over here, so don't need to write it. So this is, with that we can try to write this. Okay, so omega E is going to be I hat omega x plus j hat omega y plus k hat omega z, and omega z that's the one that's written down over there. So if we take it and the v will be x dot I hat plus y dot j hat plus 0. So I can just work it out, and let me write that down. Okay, so I worked this out, the cross product, this cross product. Now I think we're ready to write the whole thing. So the I hat component will be x double dot from here, 2 times this minus 2. I also made the correction here, there's an m missing, y dot omega sine lambda, and there's nothing from here, and this is going to be minus x over ml t equal to 0. Okay, the separation gives me these. Now from this I can further simplify. We can say z is much less than the length of the pendulum, so this just becomes t over m. This just turns into t over m, and further we can say that this is much less than g. Then we can say g, that gives me g equal to t over m, and so t is mg. I can use that in these formulas, and so this becomes mg and this becomes mg, and so the m's cancels out, m cancel out, and you have a g over L, which is for the pendulum's original frequency. G over L, let's call it omega square, del omega square. This is completely ignoring rotation of the earth. You get frequency omega square g over L, so you can use that over here. So now these two equations that we have to solve, we're going to focus on solving those equations. Okay, and there will be some math tricks I'm going to introduce. It's very easy to solve, not that hard. If you solve simple two-dimensional simple harmonic motion, that like a damped oscillator, you've seen this problem before. Okay, first thing to notice when you get all this far, you should make sure that you got the simple pendulum out from here. So if the omega is 0, there's no rotation of the earth, right? Then you should have x double dot plus omega square x equal to 0, and this will give you back and forth motion of a pendulum just on a plane, staying in this plane. So if you start in x, if this this was the x direction, it's going to just keep going back in x direction, back and forth. And if you think out a shadow, look at shadow will just, the shadow will go from here, back on the x-axis. That's what this is. So both of this is correct, and the signs are different here, and this is makes it coupled here. Aside from sign, the x variable depends on the y, and the y variable depends on the x. So we call it coupled system of equations, and they occur quite frequently in physics. So it's good to have some practice with that, and this is a simple enough problem to do practice with that. If you use complex variables, it's very easy to solve this. Without complex variables, you can also solve this. Actually, if you write this out in rho and phi, you'll be able to solve it. Okay, so one way to solve this problem is to introduce a complex variable, say q equals to x plus iy. Then solve for q. Okay, and from there you can extract x and y. The real part of q will be x, numerator q will be y. So this is one way. Another way is to look in the radial component and angular component. So you can say x equals to rho cosine phi and y equals to rho sine phi, and then you do x dot, and then do y dot, then do x double dot, y double dot, and so now then you can this equation and then this equation. So when you work this out, I'm going to write out what I'm going to get, and this you work it out, and then I will see if I got it right. Okay, now I'm going to take this, multiply by sine phi, and take this and multiply by cosine phi. So, and then subtract. So you can see this guy with this guy will cancel out, and at the end of the calculation, and then use like a sine square phi plus cosine square phi equals to 1, and then you can, after simplification you'll get this. Okay, so this is actually the projection, and the claim is that this pendulum is going to go, this plane will actually go this way in the northern hemisphere, clockwise in the northern hemisphere. So it's going to go this way. Well, the angle will be less, this way will be phi increasing, and this will be phi decreasing. Okay. Well, you can try to solve this numerically or something like that, but if this term wasn't there, it will be very easy to solve, right? So when would this term not there? Well, if phi dot is uniform, if this thing is uniform, if phi dot is constant, then this term will go away, and which is a reasonable thing. It's going around this. There's no reason for a particular angle to be more preferred than another angle. Not necessarily. Why would it speed up? So there's a symmetry in the problem. So we can say phi dot is constant. That kills this, and that kills that with that, and so d phi dt, that's phi dot explicitly writing, and b is equal to 2 omega sine lambda and this minus 2 cancels that 2, this 2 cancels that 2, and this minus omega sine lambda. So you can see that in the northern hemisphere, lambda is greater than 0 northern hemisphere, lambda less than 0 southern hemisphere. So this is equal to minus omega sine lambda in northern hemisphere, and positive southern hemisphere. And so phi is, you can solve this. Say phi at t equal to 0 is 0, so you start with x-axis. So you go back to the x-axis after some time t, 2 pi. So this is phi equals to minus omega sine lambda times t. So this becomes 2 pi when the time period for this precession. So bring it over there, and so TP is going to be now we can just make it an absolute value. It's going to minus 2 pi because it's changing and going back to the minus 2 pi. So it's minus 2 pi after one time period. So TP is 2 pi over omega omega of the earth. Let's put the omega back for the earth, sine lambda. We have dropped e just for the sake of calculation. A whole bunch of places there was omega. Writing would have been too much, and so this will be this t of the earth rotation over sine lambda, and this is what we were after. So after quite a bit of time, we have finally derived our formula, but along the way we made some simplifying assumptions, and you can be aware of how important those simplifying assumptions are. Now some of the assumptions would not work if you're going to study the like a flow of the wind or something like that, a little bit where the altitude is great or the speed is great. So movement in the z-axis is great, but for the pendulum problem it seems reasonable. Okay, so I'm going to stop here. Now if you want to check my website out, that would be great. If you can hit the like button, appreciate that. Apparently 10% of the people only hit the like button. That helps circulate this knowledge to more people. I will see you in another video. Bye.